Alright.
Are we good?
Yeah.
Okay, everybody. Welcome to our fourth and final Micromouse lecture of this quarter. Yay! Today's lecture is going to be on IR sensors. Please scan the QR code if you haven't already. Okay. Okay. So here's a quick overview of what we're going to be going over today. So, of course, we're going to be talking about IR sensors, and we're going to be discussing what they are and why exactly we use them. So there are actually two parts to our IR sensor system, and that's our IR emitter circuit and that's our IR receiver circuit. So the IR emitter circuit, that's going to be responsible basically emitting pulses of infrared light. And then in our case, it's going to be bouncing off these walls, and then when you get these pulses back, they're going to be measured by our IR receiver circuit, and that basically tells us, it allows us to see the walls of the maze to detect if we get them. And then we're also going to be discussing the software and how exactly we use the value we get from our IR system.
All right, let's investigate the IR sensors. Okay, let me review all these. I don't know why this is an animation. Oh shit! I'll go back, right?
Yeah, that's right.
Okay, so we're gonna go over how our IR sensors actually work. I mean, some of you guys might already know this. You might have already used like this, but basically, an infrared LED, which is our IR emitter, emits some light. So the objects nearby are going to reflect this light back to us, and closer objects will reflect more, and farther objects will reflect less. That's like, you can imagine that, because like, I don't know, you think of like density of light, less of it reaches things that are far away or something like that. And then our phototransistor, which is our IR receiver or our IR sensor, so those are the same thing, by the way, are going to detect that reflected light, and this is going to change the voltage, which is read by our MCU, and that's how we're going to be able to measure like how far things are and stuff like that.
So the infrared LED that we use is it's like the same as like turning on an LED, except this time it's infrared light. You're displaying that, and then the phototransistor is what we use to basically detect everything. And then if you look at that bottom diagram, basically shows like the intensity that we read coming off like these pulses of infrared light, like bouncing off the walls in our case. It's not linear, and it's like 1 over d squared. But yeah, we'll discuss more about how they work, but that's a general like summary. So wait, let me get all this shit. Okay, so why IR sensors? Have you guys ever worked with like ultrasonic sensors yet? Yeah? Okay, you'll probably be working with ultrasonic sensors a lot in your physics like lab classes, but you might be wondering, why don't we use that instead of IR sensors? Well, ultrasonic sensors, they're very bulky, so imagine having like 4 of those on your little rat, and that would be like insane. So that's like a large reason of why we use IR sensors more. It's because they're like small and compact, and you can fit a lot more. In our case, we have groupings for our IR sensors, so that's going to be an IR receiver and IR emitter. So we have one on the left side to detect left walls, one on the right side to detect the right walls, and then 2 of these pairs to detect the front walls, basically. And then not only that, they're contactless, so you're able to detect the walls from far away, which is exactly what we want. Whereas if you did use like, I think touch sensors or like, I think switch sensors, or I'm not sure, but like, yeah, but like you have to make contact with the wall, so that's bad, which is also why we use IR sensors. And another pro is that when you use IR sensors, they're giving you analog values. And this means that you're getting like a wide variety of values that you can then like set a threshold for detecting a wall. Like say you're getting a value of like 750, then you're like, hey, I detect a wall at 750. And this allows you to basically just roughly measure the distance. Do you guys have any questions? Okay.
By the way, the like opposite, not opposite, I don't know, I'm supposed to say opposite analog signals are digital signals, which, if you guys know, it can only be 0 or 1, which is why like it's important to have the analog signals.
Yes.
So the IR emitter though,
Yeah.
does it emit like just in a straight line, or does it go to the side? Because then wouldn't the IR receiver receiver just be getting light from the emitter in this diagram? Like,
What's that?
Cause like in my mind, like you have like two LEDs next to each other, which is what it kind of looks like.
Yeah.
This LED is gonna get light on the other one. And I don't know if that
Yeah, we'll
makes sense.
go over that.
How do you not get interference?
Yeah.
Well,
So
yeah.
okay, we'll discuss that more, but essentially like it doesn't like you like for all these pairings, like you want to turn like one of the IR emitters on and then like have basically one pair working at a time. Or else if you're emitting light like right here and you're receiving light from here, this light might like interfere with this one, so that's not good. So we turn on one pair at a time. But for the pairs, I'm pretty sure the IR emitter like emits it so that like, or might be at like a time interval so it doesn't interfere with like the light you're getting.
I think, are you asking like why the one doesn't right next to it doesn't interfere with the emitter right next to it?
Like,
Yeah.
Like the
yeah.
sensor right next to it?
Yeah, yeah. Like how
It's
do we
basic.
know?
It's just because it's not like it's a light bulb we hold. It goes out in every direction. It shoots out like in a cone in front of it.
Yeah.
Okay, yeah.
Like, I mean, I
Or
would
like not like an LED, because like an LED kind of
Yeah, yeah.
has like
So
a-
like this is our okay. I don't know. This is our emitter. By the way, this was already gonna be gone over, but it doesn't matter. I don't know how you spell emitter actually, so I'm just gonna stop there. It shoots out like this.
Yeah.
So it's not like it's not
is
like
it kind of like is the receiver, is that also like kind of conical or?
I actually don't know what the receiver
Yeah.
range is, but like cause like
It just receives it, and that's all.
yeah, it's receive. I mean, I might be from every direction, like or like a thing. I'm sure you can Google it and say like on the data sheet.
Also, wait, is there a slight delay? That's also why like it doesn't like sense this light.
Yeah, that's also like, I don't know if we go over that in this, but basically like, it shouldn't be too big of an issue, but like, because we have, like, we could have multiple of these running at once, we don't want, like, this is another emitter. We want this thing, this receiver to only like pick up what is like being illuminated by this light. So we keep the other ones, we keep this other emitter off while this one is emitting, so that this doesn't pick up anything from this or something like that. So once this is done, like this has read a nice value, then we'll turn it off and then we'll emit from right here, and then read right here around it. But
Wait, also,
I forgot there was a
wait, is there a
chopstick.
slight delay for like emitting and receiving? Or
No.
I think if you look at the IR transmitter receiver pair,
Yeah.
one of them is blackened, right?
Yeah,
So
yeah.
that blackened portion prevents the other receiver from like. So that's why it shoots
that's not a
that.
rule. Like there's actually
They can actually like come in like anything.
yeah, they can come in anything.
Yeah.
So like I actually don't remember which one is which in this case, but like let's say the emitter is black and the receiver is white
Oh.
or clear. I've seen the opposite.
Yeah, yeah. Like this one is just to differentiate. That's why we have these colors. But they could like both of them could be white. Both of them could be black.
Oh,
Yeah.
both of them could be.
Yeah. I'm sure there's a reason they're different in like
So what I
manufacturing
thought
sense.
was that
I don't
one
know
of
what
the
it is.
sensors blackened out except for the very tip, so that it emits in a nose cone type of fashion, and then the other, like the receiver receives it from all sides. Or like if the receiver is blackened, then the sensor can emit everywhere, and the receiver just receives.
Are you saying you know that's true or is that
No,
true?
no, I'm just giving.
Yeah, yeah.
Oh, okay.
Because I don't know if that's true.
Theorizing.
Because
Theorizing,
like
yeah.
I've said, I've seen emitters which are
Yeah, we see like
Clear.
emitters white and black.
Yeah,
like,
yeah.
Receivers
Or
white and
clear.
black.
It's
So
the black thing, the entire
Yeah.
diagram.
so I've seen
Oh.
all the variations of that.
we
So
see both. That's fine.
okay, wait. Now did I even do my slide?
That's
Okay.
cons.
Okay. That's my last one, right? Okay, so like some bad things about our sensors. Probably the biggest bad thing is like ambient light can greatly affect it, and like the worst culprit is probably the sun, because the sun emits a ton of infrared light, and so basically our Micromouse is not going to work very well outside or like in places where there's a lot of like windows like that. If any of you like saw me at some fair or something, and there was like a
Yeah,
Micromouse.
outside Bolter.
Yeah, there's a Micromouse
covering
demo,
it.
and I was trying to cover it and stuff like that. It's because I was trying to make it work outside, but it wouldn't. I guess that's like a case for ultrasonic sensors or something like that. But the upside, also like always the competition will be indoor. That's why I'm not worried about that. It requires calibration to measure actual distances. So like it kind of goes with this thing. I think there's one more actually. Okay. It kind of goes with these two things on the bottom, which is like that there are variations correlation between identical sensors and different materials, like wall materials will give different readings. Basically, like a value of like 2000 that we read from like an analog signal of 2000 doesn't mean anything except for what we interpret it to mean, if that makes sense. So like if we put our mouse 1 inch from the wall and we get a value of 2000, we're gonna like then program it to our mouse and say like, okay, if you get a value of 2000, that means you're 1 inch from the wall. It doesn't actually mean, because you could, another sensor on your same mouse could be like 700 when you're an inch away or something like that. So they're not precise measurements, it's just like you're gonna have to define what they do. And then the same thing earlier about the nonlinear scaling of distances because of how light intensity works. And it like diminishes in a squared fashion, not a linear fashion.
But basically, these readings that you're getting from your IR receivers, they're gonna vary. So like, depending on like what room you're in, you might have to recalibrate. That's like the main part.
Oh yeah, that's an important thing also. Yeah, different rooms, like especially because some might have more ambient light from the sun or something like that, are you're gonna have to recalibrate.
Yeah. So during competition,
You could have to. I didn't
Yeah.
have to do that.
Oh, okay. But like during competition, since like if you're working in the lab 24/7, you're like making sure it works in the maze, like in the IEEE lab. When you go to the competition, which is just like engineering, like probably 6, like the light might be different, so you just have to recalibrate it a little bit. Okay, now we're going to be discussing the analog IR emitter circuit. Okay. So what is this big circuit? Well, that's our IR emitter circuit. So this is actually what you're going to be designing, and I think assignment 4B. Don't worry if it looks very like big and complicated. We'll go over everything. Okay. So here's a brief summary of like how it works. We'll talk about it a lot more, but if it kind of looks familiar, you're right. It kind of looks like our motor one, right? Like how we power on our motors. In this case, we're using an IR LED to emit IR light, right? Like usually you want an LED to light up like green, blue, blah, blah, blah. But you want this LED to do infrared light. So this is gonna be our infrared light, and it's gonna be in the form of a diode. In this case, to basically power on our IR emitter, we use a transistor to turn it on or off. And this is because the MCU doesn't supply enough current by itself, so we have to directly hook it up to a battery, which was kind of like the same reasoning we had with our motors. So depending on whether the MCU pin is high, which means that it's on, it's gonna basically turn on or off our transistor. And our transistor basically acts like a switch. So if the switch is on, it's connecting the circuit, allowing current to flow, and if it's off, it's not allowing current to flow. So let's give an example here. So our MCU pin is high, that means that it's on. So it's gonna connect our IR emitter's current from here to ground. And this basically allows current to flow from our battery to that resistor to our IR emitter and then to ground. And this essentially allows our LED to be high, which means that it's on. And otherwise, say our MCU pin was low, it wouldn't connect. I mean, the transistor would be off, and there would be no path for current to travel from the IR emitter to ground, and that way the IR emitter would be off. You guys have any questions about what I just put? Yeah.
Well, what's the purpose of the capacitor and resistor?
Okay, all right, perfect. Yeah, we'll go into that in like basically just next slide.
Yeah, that can be
Yeah.
No, it's not. But
Okay.
we'll go over it
in
in
like
a couple slides.
one slide, yeah.
Okay, so yeah, I don't know how useful this information is, but that's the model of our IR emitter. The voltage forward, basically because our emitter is a diode, like if you've ever used LED, you know it's a diode, the voltage or current can only flow one way through it, is 1.3 volts. Our maximum current is 100 milliamps for the specific IR emitter, and then the wavelength which it emits is 880 nanometers, which is like, I don't know what the actual infrared spectrum is, but it's infrared spectrum. So it's also not the distance spectrum. And then like what I was saying about this earlier, it has a 15-degree viewing angle, so it's spewing out light in 15-degree cone or something like that in front of it. Yeah, so yeah, I mean that can prevent it from interfering with being like right next to it.
One important thing to note is that the wavelength is 880 nanometers. Wait, yeah.
Did I not say that?
Yeah, no, I know. But Okay, yeah, but it's that. So one thing is when you actually do make your Micromouse, right? We give you suggested parts that you guys can choose from. But if you do choose to like pick your own IR emitters and receivers, make sure that they're compatible in terms of wavelength. Because like if your IR emitters like sending out 880 nanometers and your receivers like take something else, like that's way off, it's gonna be bad. So just make sure that's consistent. But otherwise, yeah, that's basically the like specifications for
Your
IR.
receiver should have like a range, which is like
Yeah.
which is good for. So
Just make sure they
check
sync
those
up.
two things.
Yeah.
Okay.
I thought IR emitter and receiver circuits come in pairs, so won't they already come
I mean,
to
what do you mean? They could come in a pair. You could make a circuit which is like combined. I'm sure like, but like.
I think they're or maybe the ones I've worked with, they were hooked
Oh
up
yeah.
with the
You
same.
probably worked with like a small breakout PCB board that had it on it at the same
Yeah,
time,
yeah.
right? Yeah, no, we don't. Ours aren't like that. Like we literally, like your part is gonna look like this.
Like two start like wait, you guys solder on the IR emitters and
No,
receivers?
this
Yeah.
is, we haven't. That's like the sign.
Yeah.
Like this is like literally what your things are gonna look like. They're gonna look like. Have you ever used like oh, have you ever used like an LED in a breadboard or something like that, and they look like this? That's all you're gonna get. And then well, on your rack it already has a circuit, but on your own mouse you'll have to make the circuit in like assignment 4. And so this is all you have. There's no like board with the two things on it already that have like a bunch of stuff happening inside of it. So.
Yeah, but you basically just purchase these parts, so they're separate, so you might have to. But if they do come in pairs, yeah, you're free to use them and stuff. This is, now we're going to be talking about MOSFET, and in our case, we use the NMOS MOSFET. It's basically a type of transistor. You'll learn about this in your upper division EE classes. Low-key learning this right now. But essentially, like I mentioned, it basically just controls current flow from the IR emitter to ground to allow current to flow through, and it's basically necessary to turn emitters on or off because you don't want your emitters running like all the time because of power and stuff. Also, it turns on emitter when MCU pin is high, like I mentioned. Yes.
So, what have you already mentioned? These bypass capacitors, and basically, they're there to stabilize supply voltage for like from constantly turning on and off the transistor. Like if you, what other things we had? It was like our motor driver or something. We had these capacitors as well to stabilize our voltage, and that's basically what they're there for. They also reduce the turn on time, so like our IR emitters will turn on faster because the capacitors, and that's good because we want to be able to turn them on fast and turn them off quick because of like what we were talking about here, right? To turn them on real quick and then read it and then turn it off. And then the faster we can do that, the more like real time, the more real time data we can have.
How do you know when you need to include a bypass, like capacitor? How do you like originally figure out the
That's a great question.
capacitor?
A lot of like circuits, like we talked about, they always have capacitors, and that's usually just to smooth out like voltage spikes and stuff. In this case, why it's bypass? Not too sure, but it does. I think the difference between bypass capacitors and smoothing out, it's like it reduces the time.
That's my guess.
Yeah, because like
Because they have one similar function. It seems like it's an
like our reasoning why it kind of like reduces the time to turn on for IR emitters is because when your MCU pin is low, this transistor, which acts like a switch, right? It's going to be off, or which means that there's no current flow in this branch, right? But that means that there's still current flow inside the other branches, right? So like it won't go through R4 that resistor, but it'll take the other current path. And that means that when you do turn it on, it doesn't have to go from the battery all the way to this transistor and down. There's already like current flow going on like right above that node. So I think that's why like it reduces time.
And I don't know how you decide. Like we didn't make the schematic. It was like made a long time ago, but I'm guessing just it's good practice for
Yeah.
like I think this would probably work without those, but it would probably be less like refined in a sense.
Yeah.
To add
choose your capacitance? Because you guys have chosen like 4.8 microfarads.
I don't know if we can answer that. Like, yeah, I mean, because this, I mean, again, this circuit we didn't make. It was made a long time ago. Either, because like, okay, a lot of the time, like, okay, these values don't necessarily are like perfect values. Like, if I was using 4.8, what is that, microfarads?
Microfarads.
Yeah. If I was using 4.8 microfarads capacitor, like this wouldn't work at all. Like, it would probably work the same, basically. So either the people that made it did some calculations and were like, these are the closest things, or like they just guessed or something, or like experimented. I'm guessing they did some rough calculations and this was like fine or something.
Also, why like two capacitors in parallel? Why wouldn't like one capacitor like not suffice?
I don't actually know. I mean, different capacitor values might have like maybe like maybe a more robust effect or something like that.
Yeah, I'm not too sure, but I think like,
Because they're like in parallel.
wait, most smoothing capacitors aren't they always in parallel? Or actually no. Yeah, I'm not too sure. We're not too sure.
The last moving capacitors for the H scheme, those are in,
Were they in parallel?
yeah, they're in parallel.
Yeah. That's a good question.
Sorry, this might be like out of like the scope, but you talked about like the MOSFET, is
Yeah,
it?
yeah.
And then I've also heard like PNPs and NPNs.
Yeah.
Is there like in like a really like kid friendly way, what is the difference?
Okay.
Why do you use a MOSFET?
Do you first
Alright,
answer?
wait, so you, okay, so in short, PNP, NPN, and MOSFETs, they're all types of transistors, right? So they all basically just like connect it or don't connect it. The difference between PNP and NPN is the type of material that's used. So you'll learn about this, like, dang, you're probably gonna learn about it like they're here like I am right now. But they're like different types of semiconductor types. So like NPN, it's gonna be like N doped and then P in the middle, which is positively doped and negatively doped again. So, sorry, it sounds confusing, but basically the different materials for NP and PNP. That's like the main difference. And then for MOSFETs, the difference between that is like, let me see. I can't explain it that well, but shoot.
That's okay.
Yeah. But they basically just act like a transistor. Yeah. If you want, after this, I can show you exactly like a MOSFET diagram and explain it. But yeah. I don't exactly know how like they function differently, but they do act like basically a transistor, like a switch. Okay, now we're gonna be talking about the MCU pin current limiter. So that's basically just this one resistor right after the MCU. And what it does is basically it limits current flow from the MCU to the MOSFET gate. And basically without this resistor, there'd be too much like current that might potentially damage the MOSFET. So that's why we have a resistor to basically limit that. Okay.
Alright, and then here's another resistor. So here's another resistor called our pull down resistor. So basically, this is going to, let's see, keeps LED off and it's pins floating. Keeps LED off. How would that affect LED on or off? Anyways, well, one thing it does is basically, when our switch is, or when our MCU pin is not applying like voltage anymore, and so there's no more reason for current flow, the current can't flow back to the MCU pin, and so it needs to flow somewhere. And so rather than like, oh wait, that's what it is. Yeah. So rather than it like applying voltage to the base of the transistor again, we want it to instead flow down to ground, and it's going to do that through this resistor. And the reason for the extremely high value here, like if you notice, like this is 47 kilo ohms, which is a lot greater than 100 ohms and 51 ohms if you're using for the other two resistors on the circuit, is because we want to keep the current draw low when the MCU pin is actually applying voltage. So like if you notice, I mean, okay, I'm just gonna walk over here. So basically when the pin is applying, or okay, when there's current flowing through here to try to get through to the pin, it also wants to flow through here, but because of the extremely high resistance, a lot less of the current is going to flow down through here, then it's gonna go through here. Like if this was a lot lower of a value, the current would have a lot easier of a time flowing down through here. And we don't want that. We want most of the current to go through here. If that makes sense. Like, I mean, if you guys know like V equals IR, you know why that makes sense. And also, the reason we have this as opposed to, it kind of goes into the explanation I was just saying. The reason we have this as opposed to not having this, because imagine there's no resistor here and it's just a wire, is because then if we applied our voltage and there's current flowing through here, we just flow through here to ground instead of going to the base of most things.
But basically, just to restate what Michael said, it's basically we're explaining like why we need this path at all. Like, would it still function even if we didn't have this path to this path? And that's because right when you turn off, say the MCU's on, right? Right when you turn off the MCU, current's still gonna be going here, and then the voltage here, there's like current that's here, has a path towards ground, but then what about like excess voltage here? Where's it gonna go, right? You don't wanna accidentally like turn on your LED, so for a way to basically like dispose of the charge here, you have to make a connection to ground, which is exactly why we have a connection from here to here. But then this leaves it because there's like a short, and you don't want a short because then it'll never take this path at all, which is why we need a resistor. And then with this resistor, then charge can go from here to here when the MCU's off. And the reason for why it's high is because like we don't want, when it is on, we don't want any current to be going through here. We want like most of the current to be turning on this transistor. Does that make sense? Okay. Okay, so now we're going to be talking about the LED current limiter. And what is that? Well, that is just our little resistor at the top. So basically what it does is it limits the current through the LED, since the battery's current is like, it can be potentially like very high and dangerous. So we want to limit that with our resistor. And how do we exactly calculate for this resistor value? I know we weren't able to calculate for our capacitor values, but we are able to calculate for this resistor value. And the voltage that our battery is supplying, also represented by VCC, is 3.3 volts, right? And our ideal IR emitter forward voltage, it's called forward voltage because LED, it's a light emitting diode, and diodes only, like, they only want current to flow in one path, so that's why we just call it forward. But ideally, we want this voltage drop to be 1.3 volts, right? So if the voltage drop across this IR emitter is 1.3 volts, where does the extra 2 volts come from, right? So we have to make sure that it drops an additional 2 volts for our resistor. And basically what this is saying is 3.3 minus 1.3 volts is 2 volts. So besides this IR emitter voltage drop, we have to somehow like drop this voltage again, and that's where we have it in our resistor. And our desired current through our through the, what's it called, LED is 40 milliamps. So if you do V equals IR, you're able to calculate for the resistance we need so that it'll reach like the optimal voltage drop. Does that make sense? Hopefully. Okay.
Basically, like if you ever turn an LED on a breadboard, you have to put the resistor first. That's what this is here, so that we don't like destroy the emitter.
Well, a lot of times in these circuits, like just like filling it up with resistors to make sure that it's like safe. But this is like the last slide for our IR emitter. Do you guys have any questions, or do you guys want like general overview again? You all good? Yeah.
What's the general like current flow path? Does it start from the 3v3
Yeah.
and then goes down and then goes to that?
Always remember that current is going to flow from our high voltage to low voltage. So ground, by the way, is like low voltage. It's always, or it's usually considered 0 volts. And so 3v3 volts is 3.3 volts. So it's going to flow from 3.3 volts all the way down to ground. And then I guess also there's the voltage applied to the MCU as well. Is this like?
Yeah.
Okay,
Okay. But this is general path. So say like a lot of what you just like said, like, oh, like which path does current take and stuff, it's dependent on this MCU pin if it's on or off, right? Let's say it's off, there's gonna be no current like here. It's all gonna be on the right side. So it's just gonna go through the 2 capacitors and then to ground, right? But as soon as we turn on this MCU, it's gonna allow current to flow in this branch, in which case it'll turn on the IR emitter, flow down to the transistor, and then back to ground. And then right when you turn it off, this path is gonna be closed again, and then leftover charge is gonna go from this to ground through that resistor.
Got it.
Okay. All right, let's look at the IR receiver circuits. Okay, let's apply all of it. Okay, so our phototransistor, which is what you see, which is that Q1 thing. If you, I mean, actually it's in the name. I'll just say if you look at it closely, it's also a transistor. So it's going to act like a switch, but instead of like applying a voltage to the base, the amount of the amount of IR light that it receives or that's reflected off of an object is going to control how much current can flow through, through the transistor and then also through the resistor. And so depending on that current that the transistor allows to flow, there's going to be a different voltage drop across the resistor. And then the reason that voltage drop matters is because that voltage drop we can measure with our MCU's ADC functionality, which is analog to digital converter. So let's see. So basically, basically the more reflected light that the transistor receives, the more current which is allowed to flow through here, and then the more current that's allowed to flow through here, the greater the voltage drop across this resistor is going to be. So actually, you can imagine more like the greater the voltage is going to be right here, if that makes sense, because of V equals IR. And so so in case you don't know, I guess it's saying it like V equals the voltage, I equals the current, and then R is the resistance. But basically, if we increase I in that V equals IR, the voltage here is going to be greater, or the voltage drop across this, because this is ground, which is 0, is going to be greater. And then we can measure that, which out, by the way, is going to our MCU's ADC, analog to digital converter. And that's how we're going to read the
How does an ADC work?
So ADC, analog to digital converter. We're not, okay, the MCU actually handles all of the conversions,
Yeah.
but essentially, like what you're getting in this output, it's gonna be a range of values in terms of voltages, right? But we want like defined values, so like digital values, like 700, blah, blah, blah. So it's gonna convert like a range of voltage values into just like digital values that you can like read, like, 500, 800. Yeah, I'm not exactly sure how exactly it converts it, but
Yeah, well,
I think
let's imagine, so like, remember I mentioned digital signals earlier? If we only connected this to like what's it called? A digital, like, I don't know, receiver pin or something like that, it's basically just gonna be 1 when there's a sufficient amount of light and then 0 when there isn't. Like actually, if you've ever used an Arduino with like a phototransistor or an IR receiver, if you ever, like, I don't know if you know, like, you know, if you have to do like analog read and digital read from in your Arduino. If you were to do like digital read to your phototransistor, it's going to do what I just said. It's going to be like 1 or 0, which is not helpful at all. And so, I don't know. I'm guessing based on the strength of this, that's how it handles something.
it'll somehow just like,
the digital
I think each like ADCs, like it depends on like what type of ADC you're using. Like the type it converts from like voltage to like actual like digital values. I think it's all dependent on like the type of ADC you're using. Like some can like range from like 0 to 1,000, like the values that you're getting, or like some can range from like 0 to 100 probably.
So just to clarify,
Yeah.
you're getting analog values.
Yeah.
And you convert them to digital values.
Yeah.
But don't you want analog values for your IR sensors in general?
Okay, I guess, okay, here's like actually what it means. So like your MCU can only process digital like signals, if that makes sense. And so this analog to digital converter is going to convert the analog value or the analog reading into a digital value. What this is going to actually look like. I guess I can know this much. Like, So like your analog value, let's just say like voltage, it's gonna look something like, I don't know, like this, and then like, I don't know, and then it drops down or something like that. Let's say like at some state it's like pretty steady or something like that. What the way it's gonna convert this to like a digital signal is basically it's just gonna change like the frequency of the signal that it's sending. So like let's say like for some low voltage it's measuring, it's gonna send something like I don't know, it's gonna send something like this. I don't know if the frequency that it's or the amount that it's on. I'm just gonna say it's the same. It's just purely the frequency or something like that. Okay, you see that? So like basically it knows the frequency here is like really slow compared to when there's a high voltage. It might send something like this or convert something like this where it's like really fast or something like that. And so that's how like your MCU can differentiate between like the values in a digital format. Does that make sense?
I think so. So basically, you just change the kind of like the duty cycle to match kind of the.
So like in the analog like system, there is no like it's not really a wave, if that makes sense. But because of like how it works to process things in like or how to represent things in a digital format, like think about it. This thing can only be 1 or 0, right? And so like it can't how would you represent something which isn't 1 or 0 in such a format or something like that? And the way in which it's done is by manipulating frequency and stuff like that.
So basically, how much it's on or off kind of
Yeah.
shows.
And like the amount of time between that and stuff. So yeah.
So then you get these. It puts in a digital like value for you to read like into the microcontroller.
It will do the whole conversion for you. So like when you actually read the digital values, it's gonna like give you like a value from like 0 to like I think they go up to like 2000 something, or the ones that we use at least. But like internally, it's representing, it's getting those numbers from the 80s, the analog to digital converter converting something which is like totally not digital to something which can be digitally represented.
Is it because the microcontroller might not be able to read the analog signals?
That's exactly it. It can't read it. If you told it to read it, it would just like, it would basically just say like, this is on. So it would represent, it was like what I was saying with Arduino. Basically, let's imagine this was low at the start, but it was like varying and stuff. And then like, I don't know, you take it out into the sun, it would just read like this. Which in this case is like, works out pretty well. But like, what if it was something like this, which was like a slope or something? In the actual like, what's it called? In the actual microcontroller, if you give it something like this, it doesn't actually know anything. It just has some arbitrary cutoff point, like right here, which is gonna say, okay, this counts as a 1 now on this side, and it would count it as a 0 on this side, which is not helpful at all. We want to like be able to know. We want to have way more precision than just a 0 or 1.
So because you can't kind of like read, it can only read like discrete square waves. It can't read the like analog signals. Is what you're saying?
Yes, I don't think it's necessarily like reading. Actually, I guess it is reading these. Also, you say digital or analog, right? It's digital.
It can only read like these discrete digital like square waves.
Yeah. And it's not. Yeah. That's exactly it.
Yeah. Okay, but in summary, this circuit, basically there's one key like takeaway that you guys get from all these circuit schematics. This transistor acts like a switch. So in this case, we're using a phototransistor, still a type of transistor, in which this case, the input to turn on or off this switch is gonna be the IR light that we're receiving, right? And this will control the amount of current that actually like flows through everything. And like as Michael mentioned a lot about like V equals IR, you'll just get different voltage outputs that correspond to the measured like IR light that you're absorbing based off that. Okay, we're gonna be talking about it more. So our phototransistor again is Q1. That's like the model number that we actually use. It reads best at 870 nanometers of light, but it can read between like a range of values in which this is 740 to 1080. Like I mentioned before, try to make sure that your phototransistor and your IR emitter, they're like the same wavelength. I think when you guys do pick out your materials, we're gonna have recommended materials. So you could just use ours, or you can find better ones if you want. But just be on the lookout for that. For this, our maximum current that we want through our motor transistor is gonna be 50 milliamps. Don't worry about max surge. And then the max collector emitter voltage is gonna be 70 volts. But key takeaway, basically, the more IR light you get, the more current you're gonna allow to pass through Q1, which will then allow you to have a higher output voltage, which will then get converted from analog to digital.
All right. Let's see. Isn't this like? Oh, did I explain this on accident earlier?
Oh, maybe. Wait, this has kind
Okay, basically, it was what I said, which is that, or really what you just exactly just said, which is that more current pass through Q1, which is a higher voltage drop over R1, which is what we can measure. Let's see, choosing a value.
Wait,
Oh.
this is something you guys don't
Yeah,
understand. Like, we're taking the output right at this, but because this is like the voltage drop across this resistor, right? Since this is ground, it's gonna be at 0 volts, and then that means that whatever voltage here is dropping across this resistor, and that's what we're taking as the output. But that voltage will change depending on how much current is actually like allowed to pass through. Because V equals IR, where I changes, so V also changes.
Yeah, then it looks like this choosing the value part is like, I'm not gonna go through it exactly, but you see on the bottom it says like choose a value, which is greater than 65 ohms, and then it makes like some seemingly arbitrary jump to like 1.8 kilo ohms, and that's like kind of what I said earlier, which is like, we can change it, we can tweak these values. I don't know about a lot. We can tweak the values, and like the functionality usually just like doesn't change. Usually it's like the high ends we need to worry about, like something which will destroy our component because it's not made for it, but not like the low ends. Although you have to worry with low ends in some cases. Like you don't apply enough, or if there's not enough current, then you'd be part of like nothing. But usually there's a large range of values which it operates safely.
You guys have any questions about this circuit schematic or anything? Move on. Okay. Okay, so now we're gonna be discussing the software. Exactly how do we kind of like code this thing or kind of use the values that we're getting. So this will be explained in much more detail if you look at assignment 4. By the way, we're gonna drop assignment 3 and 4 tonight, so be on the lookout. Yeah, 3 and 4. So
we should have released 3 last time, but we forgot.
yeah.
But it's still fine. Like, what's our 2-1 due?
Friday.
Friday?
Yeah,
So
we're
like,
yeah.
technically, we'd still be on track and stuff like that.
Yeah. But
We
yeah,
don't have any more
assignments are-
lectures, right?
Huh?
We don't have any more lectures.
Yeah, no more.
Yeah, this will be it. So it's just gonna be like working, but we're gonna have assignment 2 like it's due this Friday, and then next Friday assignment 3 is gonna be due. Basically what you're gonna be doing is first like turning on an emitter, and then you're gonna be able to read the receiver several times to basically get an average value, and then you're gonna turn off the emitter and move to the next emitter. So, okay, what I mean by this is basically, you know how we have pairs of IR systems, of IR sensors, kind of like an emitter receiver, an emitter receiver, emitter receiver. You're kind of gonna be sweeping along like all of the pairs one at a time. So you're gonna be turning on one emitter and then seeing the values that it reads for that receiver. And then after you get that, you're just gonna be moving like around until you get all these readings. They'll be in like quick succession of each
Yeah, it's like really quick, so that's
Yeah.
equivalent to like doing all of that.
Yeah.
Functionally, how long does it take, like, usually to?
It's like
Really quick.
It's
I don't
like-
remember.
it's
It's
like
like really
microseconds,
small
yeah.
unit of time.
Yeah, it's really small. It's like
It like says on the assignment.
yeah.
I just don't remember that. Okay. Okay. This is like okay, so like even though, like, so we converted this to a digital signal, and then like we're interpreting it as a number and stuff like that. And it's kind of ironic how we're then going to detect walls, which is we're going to basically just set a threshold on our like number, on the number we get, and we're going to say like, okay, after this point, we're gonna say we're gonna interpret that as a wall being there, and before this point, we're gonna interpret it as a wall not being there. You're gonna interpret this experimentally. Like remember earlier I said you place it 1 inch from the wall, and then you're gonna read the values. Then you say, okay, that means a wall is to the left or something like that. And then anything less than this is not a wall or something like that. And so you can move there or something.
Basically, you're gonna be setting like a wall threshold where you want your mouse to say, hey, there's a wall I want to turn. It's basically saying, when do you want to turn? Like, look, like you can still detect a wall from this, like, say this is my wall, right? Like you could detect a wall right here, but when exactly do you want to turn? So you're gonna set a threshold, like, say then, like, once I'm this close, then I want to turn, so you want to say, hey, I detect a wall, like, at this value. And all these different values, I mean, it's just gonna be a lot of values that you're just gonna have to, like, see when you want to turn. Yeah.
How are you gonna know the distance to the wall though, or is it just, you just set the threshold at 10?
So wait, we'll talk about that, but essentially you're gonna be placing your mouse like a given distance away from the wall or away from the wall and like turning on your IR emitters and receivers and seeing what values you get at that exact location and where exactly you want it. Like you're gonna be setting it at the distance exactly you want to turn at. So
If
it'll
you
be
need,
pretty
like
easy.
if you're asking for precise distance stuff, you're not gonna do that because these are not accurate enough for that to be like really reliable.
So then what about like just?
So basically, you're just gonna. It was what he just said. Like you're gonna. Here's how you actually do. You place your mouse in the maze. You're gonna connect your ST link on the back of it, and then you're gonna. It's like run debugger as or whatever. I don't know if you guys have done the motor one yet, but like if you had to run like the live expressions thing, you can read what IR values are there live, and then you're gonna say, okay, so it reads like 2000 at this spot, and then you'll be like, it generates to like, okay, 1900 or something. Anything greater than 1900, I'm next to a wall or something like that. Well, it's not just about turning; it's about like wall detection in general. So like when you're making your picture of the maze, that's how you know there's a wall next to you. And so it's honestly more precise than like exact distances because like you know those exact like values and stuff like that. Let me ask.
So do you have to recalibrate every time you're maybe like
You might have to. I didn't really have to last year, but it could depending on the ambient light in the room and stuff. Like I think it was because I finished at night and the competition room was in pretty much there's pretty much no sunlight in it, and so it ended up being that like the IR values were pretty much the same. But yeah, you could have to recalibrate.
But it shouldn't be too hard. And also I think during competition will give you time to like set up your calibrations, you know.
So yeah. There's also if you're really advanced, like you can add functionality to that. Press a button. Well, like you place it in the spot in the maze, you press a button, then it will save those like this is how far I should be from the wall or something like that.
But this is all just to like detect walls, and like eventually you're gonna use these values to like for your algorithm, and then like where you kind of just like make like an image in your like mouse to see like where's the wall, where is it?
That seem good?
Okay. Here's some software tips and tricks that we kind of went over, but we'll go over again. Make sure to add a delay between like turning on your emitters and reading the IRs, because like the phototransistors, they don't react immediately. So also, wait, it kind of goes in line of what you were saying, like, oh, like what if the like receivers like are like getting the light from the emitters? Well, there's a slight delay, so that's why. It's like required of like 60 microseconds for value to stabilize, so try to do that because it's not instantaneous, right? Also, like we mentioned before, only turn on like one emitter at a time or like one pair at a time and kind of like sweep through all of the pairs. This way it'll keep like the phototransistor from accidentally reading from another emitter. And like a delay between separate readings can help with this, but at the same time it's instant. And last thing is, don't read the IRs in your PID control functions, because Systic like shouldn't take very long to run. I think Systic is what, like runs every or like
I don't know. It runs very fast.
it's like
basically like you can update the IR values like outside of this, if that makes sense.
Yeah, but basically Sysdig, like, it basically like allows your functions to run like every millisecond. So if you want to do something continuous, you do it in Sysdig. But if you're reading IR values, they might take more than like 1 millisecond. So you want to do that outside, or else it might break things. But that basically concludes our lecture. Do you guys have any questions? Okay, we're chilling. All right, wait, just a quick. Oh yeah.
Oh, so why do we really need the sensors on the side? Because I get the ones in the front, it tells you how far you are and how many you're carrying. But if we're using CID to stay straight, then like, what are the side?
Okay, the side ones, like say I'm going in, I detect a wall here, right? If there's a wall here, like you want to be able to detect that. That way you can only go right. You know what I'm saying? Is it?
He's saying like.
Oh, okay, I understand.
Yeah, you don't have to.
There's many reasons though.
Like it's just to detect the whole system.
But also just like
Okay, yeah,
like
that was a good
remember
question.
we said,
You're good, you're good.
remember we said like we're trying to inside your mouse eventually you're gonna make an image of your maze, which is gonna start out like this. This is gonna be your mouse. It's gonna start out completely blank, right? And so every time you move forward, I mean, unless you rotate it all around, like if you rotate it 4 times just to look at every wall around you, you can do that I guess with just the front. But otherwise, the way you're gonna know where walls are is from those side ones and stuff. So then you're gonna construct it. At the start, it's gonna say, okay, there's one here, and it's gonna move forward one. And it's gonna say, okay, there's one here. It's gonna move forward one. And it's gonna say, oh, there's none here. There's also none here. Okay, move forward one.
It'll help you just see every wall in the maze.
Yeah. So many reasons. Also, you can use it to better steer. Like if your encoder PID is trash with like lines.
Okay, why do you need multiple IR like emitters and receivers? Why can't you just have one?
You could just have one if you really wanted.
It's just like it's more accurate, it's more precise.
Yeah. Like I think in I don't know if it says it this time, but at least I just have.
Yeah. You would usually average values. That's why. Okay, but we're gonna be dropping these assignments. We're gonna be in 4A. You're gonna be soldering these IR circuits, and then 4B you're gonna be designing the circuits that we went over, and then reading analog values from the IR receivers, and then we're gonna be navigating the maze. And this is the final push between the rat competition. So on like Monday, December 2nd, which is tentative, we're gonna have like a kind of like a mini Micromouse competition. Where you're gonna be trying to just like.
No, I think actually it might be hard to put it. No, I think the way it works in that one is at that point you have no maze solving capabilities, but you do have the abilities to be like
To move
there's
around
a wall
maze.
here in front of me. I'm gonna turn right. I think that's the algorithm. It's like turn right, and then if you can't turn right, turn left.
Yeah. But it'll be really simple. It's just like a fun little way. I think we're gonna have prizes for this too. Might be
Yeah. And then like probably I don't know what it says the deadline for these, but the deadline is probably just that day.
Yeah.
And then we'll lose the final 2 assignments, and you should be diligent because like what we're on week 7, and there's only like 3 weeks until then.
Wait, we're gonna be assigning like assignment 3 and 4 are like it's a lot compared to like assignment 1 and 2. So
That's
like
a great thing to tell them.
yeah, so make sure you stay on top of it. Like we'll try to help as much as
I think assignment 3 is entire, or the like in-person one is like entirely software. So
Yeah.
no software. So if I remember correctly, that is. Okay.
Okay, just gentle reminders. Assignment 2A and 2B are due this Friday. Assignment 3 and 3B are going to be due next Friday. And ideally, assignment 4A and 4B, they're going to be due next Friday, but it's Thanksgiving break, so we're going to have them due next Wednesday. So it's low-key, it's going to be a grind. Hey, feel free to ask for extension, low-key.
No, I'm there on Friday. From,
Yeah.
Or we're both there on Friday from 12 to 4. So
Yeah.
I'm locked in.
See, yeah.
Work session. Oh, there's a work session next Tuesday, I think, at 6.
Yeah, next week. We're going to be hosting more work sessions
Yeah.
for you guys to be able to do this. And yeah.
Alright.
But thank you guys all for coming. That's it.
Yeah, and this next time stuff is for.
This is our final lecture. Hey, next work session, we're gonna get snacks this time.
Alright, you can do that.
Thank you so much. Oh wait.